Hello, David Harper of the Bionic Turtle here with a brief tutorial on two key ideas in quantitative finance, covariance and correlation. Let's take a look. In order to understand covariance and correlation, I'd like to draw an analogy to maybe more familiar idea, which is variance. In previous tutorials, I've talked about how we typically treat something like an asset return as a random variable for purposes of modeling. Now, if we want to consider the dispersion of the random variable, we will look at its variance. So variance is a measure of dispersion, or sometimes called scatter. Now, if we have two random variables and we want to consider the relationship between them, the strength of the relationship or co-movement, how do they move together, we'll look at the covariance. The problem with both the variance and the covariance is, although they are mathematically convenient for us, they are not intuitive to us humans that use these measures. So what we do is we translate them into intuitive measures. In the case of variance, we take the square root and get the standard deviation, because where the variance is expressed in units squared, the standard deviation is in units, and that's understandable to us. The covariance we translate into the correlation coefficient, which is unitless. So it runs from -1 to 1.0. So because it's unitless, we can automatically understand it. We automatically understand that the closer it is to 1, the greater the strength of the relationship between the two random variables. So that's the analogy I'd like to draw. In other respects, really, you can almost say these are the same. The variance is pretty much the same as the standard deviation. It's just translated into units we can understand. And the covariance is a direct relationship or function of the correlation, and the correlation is unitless. If we look at the formula for the covariance, here it is. It's denoted by sigma sub x and y. So that says the covariance between x and y. Notice if this were the covariance between x and x, that would be like the covariance of x squared, which in fact would symbolize variance. In other words, we can also say that the variance of x is the same as the covariance of x with itself. But getting back to this, if we take the covariance between x and y, we could also write it this way. It equals the expected value of the product of these two differences. The first part is just the individual x observation minus the average of the x's. The second part is the same, just applies to the y series. The individual y observation minus the average of the y's. So the covariance is just the expectation of this product of differences. Now remember, I said all the correlation is it's just a translation of this covariance. That covariance is the key measure of strength of relationship between x and y, but we want to translate it into a measure that we can understand. In order to do that, we calculate the correlation coefficient, almost always denoted by Greek rho, R-H-O. And so notice the correlation coefficient rho equals the covariance between x and y divided by the product of the volatility of x multiplied by the volatility of y. And so that's the key formula, and here I just put it in English terms. The correlation is equal to the covariance between x and y divided by the standard deviation of x multiplied by the standard deviation of y. We could also just simply multiply that out. If I take this denominator here and multiply each side by the denominator, then it'll go over to the left, and I'll be equal to what will result is this truism right here that is a key building block in fundamental finance. We will see this in portfolio theory. It simply says that on the left here, the correlation multiplied by the volatility of x multiplied by the volatility of y is equal to the covariance between x and y. So if that seems abstract, I'll do a brief example here. I'm going to have it's a brief set of 3 data points where I have a series of x and a series of y. When x equals 3, y equals 5. When x equals 2, y equals 4. If you look at this, I deliberately set them up so they move in lockstep. See how y is always 2 greater? So intuitively, you won't be surprised to expect that we're going to get a correlation coefficient of 1.0, perfect correlation. But I wanted to just show how the math works. So here's the covariance. We first have to do that. It's the expectation of these products. That simply means it's what's the average of these products. So we need to do that 3 times. Here's the average of x. Here's the average of y. See how we have 3 x's, 3, 2, 4. The average of those is 3, right in the middle. We have 3 y's. The average is 5. It's right in the middle. Then we need to go like row by row here. If we take the first one, all we're going to calculate is this term right here. See how that's what's inside these parens? It's the product of these differences. The x observation right here, that's 3, minus the average x, that's 3. That gets us 0 here in parens. Then we move over to the y's. What do we see? A y observation of 5 minus the average y, which is 5. We have a 0 in here as well. 0 times 0 equals 0, so we get 0 here. Now we need to do that for the next set of x and y. For the next set, we have a 2 for the x minus the x average, which is still 3, so we have a negative 1 for this first parenthetical. And then we go to the y and we have a 4 minus the average y, which is still 5. 4 minus 5 is negative 1. So we now have negative 1 multiplied by negative 1 equals 1. I can do it one more time. 4 minus 3 is 1. 6 minus 5 is 1. 1 times 1 is 1. Now I just did that. I just did the product of these differences for all 3 sets of observations. Now, what's the expected value of that? Well, in this case, it's the average. The average of 0, 1, and 1 is 0.67. If I add them together, I get 2. Divide by 3, I get 0.67. And what I just did is calculated the covariance. The covariance, if we use these 3 sets of observations between x and y, is 0.67. So we're done. In a sense, we're done. We've calculated the relationship between x and y. The problem, as I said, is we don't really know what that means. We just know it means the positive relationship. We're not sure how to make sense of it, so we translate that into the correlation coefficient. And you remember, all we really need to do is divide this covariance by the product of the standard deviation of x and the standard deviation of y. Now, I won't do the standard deviation for you right now. I'll just show you that it turns out the standard deviation of x for this 3 series in isolation, we're only talking about the x right now, is the square root of 0.67. Also, the standard deviation of y turns out to be the square root of 0.67. So now if I take the covariance, 0.67, divide by the product of volatility of x and volatility of y, if I multiply the square root of 0.67 by the square root of 0.67, I get 0.67. So that denominator is 0.67. So I now have 0.67 divided by 0.67 equals 1.0 for the correlation coefficient. See how I did that? Take the covariance divided by the product of this times this equals 1. Our correlation coefficient in this example equals 1.0, so we have a perfect positive correlation. That's only because I deliberately set it up so that y is always in lockstep with x. We'll never see this in real life with real data. But I just wanted to show you how we get to that correlation coefficient. And that's a unitless measure we can now understand.